Well, hello again, Year 10, and we're going to do the investigation of the conservation of momentum. I think this is spreads 10.3, 10.4 in your physics textbook, if you can get online on Caboodle. Don't worry if you can't. And so there's your learning objective for today. And we're going to be building a couple of bits of equipment. I've got two bottles, and they are suspended on pieces of string, and the bottles have different masses of water in. For the sake of argument, I'm calling that my red bottle and that my black bottle, simply by virtue of the tape that's on them. The bottles are hanging from a support. Now in your house, the way I've done this in mine is I've managed to put a chair on its back on a table, and that is holding the bottles up. Now obviously if you're going to do this at home, please ask your parents first before you put their precious furniture upside down on tables. But hopefully you've got an old chair, or a chair that no one minds you doing this to, and you can hang the string and you simply tie it around the bottles. The bottles are hanging very close but not touching to each other. Behind them I've got a ruler. You could just as well put anything that can have marks on it, and the stop clock is simply there for effect, but I'm going to try and use it in a moment. And you'll see I've got the headings of a table on the board, and here we've got behind, you'll see we've got volume. Now the bottles are in the way, so it's going to move the top bottle out of the way for a moment. So I'll put that up there. If it comes hammering down in a minute, don't worry too much. So what are my headings? I've got vol, which is the volume of the bottle. They've got volume readings on them. They're 330 ml or 500 ml. A distance in centimetres that the bottles are going to move. A time, you can just see that either side of the string, in seconds. Velocity, distance divided by time, remember, centimetres per second today. A mass, which is going to come from the bottle, and I'll explain that in a minute. And then we're going to work out the momentum, and the momentum is the product of mass times velocity. So whenever we come to momentum, it's the mass times the velocity. And that's the first learning thing for you today. If I can manage not to put my T in the wrong place. Okay, so next bit. I'm then going to need to take some measurements to fill in my table. So you can stop the video and draw your table and then turn it back on, but obviously I'm going to carry on going. And the very first thing I want to do is take my first bottle, which this is my lighter bottle. The black bottle is my lighter bottle. It's got about 150 ml of water in it, and it hangs just above the red strip on the board. And I want to know how fast that moves when it's swinging, like so. How fast is that moving? And to do that, I'm going to measure how far it is from here to here, and measure how quickly it does that. Now, it's quite difficult to do this live on camera, but you'll get the idea when you try this yourself. So I'll stop my little clock and reset it. I'll hang it there. I'm going to go start, stop. Well, no, I'm not. I'm going to do it again properly. So I'm going to try and let go of it cleanly. So I go start, stop. Again, I did that too slowly. It'll take you a few goes to get this right. Start, stop. Too slow. And so after you've done this 10 times, start, stop. But obviously I'm moving my hand to the wrong button. So you get the idea. I'm going to time how it goes from there to here. And if I can do that correctly and go start, stop, again, you're going to love doing this yourself. So try and get one reading. So I'm going to start and stop, start, stop. And that's effectively what I'm trying to do, is that bit there. You get this. It's important you get the idea. Do that 10 times so you're absolutely certain you're measuring that time. Then bring down the other bottle. Now when these two come together, this transfers its energy to the heavier bottle, and that moves. So I go to exactly the same point each time, and I let go, and it moves. Now the hard part is I need to know how long it takes to go out there and come back. So watch again. I'm not trying to do this in front of the camera, but that movement, I need to time that. It's a very short time, but it's quite feasible to do it when you practice it and you're not under pressure. So from there to there, I need to know how far that's gone. Now, you can either try going from there and back again, but it's better just to let it go out. So I just want to know, let's be quite clear, from there to there. And to do that, you're going to have to take the time, first of all, use your by eye to see where it suddenly starts to come back, just want that time. And when you've done all the timings, then do your distances. So put it back to exactly the same place as it was last time. Make sure you know where your cut-off point is. That's easy to measure. The second one's much harder. You have to watch the bottle where it is, and as this slams into it, it moves. Watch where it goes out, and just before it starts to come back, you take that reading. So I want that distance, that time, that distance, that time. I'm sure you understand that. So that gets my raw data, and you can then put it into your table. So let's, as always, remove one of my weights and remove this. And now you can see a set of results. So looking at the results now, we've got a volume here, 500 and 150 was in my bottles, and then I've got a distance. Now when I did it, it went 3 centimetres. The other one went 28 centimetres, the lighter one. The time for this one was 0.18, the time for this one was 0.6. Now when I did these readings, I did it about 8 times and took an average. So these are average readings you're seeing. I'm not bothering to show you that today, but you're quite capable, you're quite intelligent to do this. You've seen how hard it is to take the readings. It's quite a sophisticated experiment, but it does work. And then here I've got my velocity. The velocity is distance divided by time. So that distance divided by that gives me this, and that distance divided by time gives me this. So I've now got my 2 velocities. And then now we come to the idea of mass. If you look on the internet, if you Google it, 1 milliliter of water weighs 1 gram. So a 500 milliliter bottle actually weighs 500 grams. That's really useful to know. And a 150 milliliter bottle of water is 150 grams. And the bottle's made of plastic. It's approximately the same plastic in each bottle. And I could have used identical bottles. I only had 2 in the house I could play with anyway. So then we come to the working out momentum. Mass times velocity. And so I take my mass, multiply it by my velocity, and what I get are these numbers here. 8,000, and the units, grams, centimetres per second. I'll come back to that in a moment. This one, 6,900. Now, when you look at these two, if there's no energy lost in the experiment, and there shouldn't be, these should be identical. So the fact they're different is not surprising. After all, that's the whole point of a practical experiment. Now, your job is to try and do this experiment at home more accurately than I'm doing it, and see if how close you can get these two. Now, what I put here, 8,000 grams per centimetre per second, is the same as 80 grams per metre per second, because I've divided this down by 100. So that's where that one's come from. And then take it down further, 80 grams per metre per second is 0.08 kilograms metre per second. And why I've done this, well, you could get a question in the exam that gives you that number and asks you to express it in that, and they expect you to move the decimal 0.5 places, etc. and so on. And you've got to be conscious that they're going to ask you to do this. It's easy to do in steps. And so in my experiment, approximately 8,000 versus 7,000, it's about a 12% error. It's probably too high to be acceptable today, but I'm showing you real results from a real experiment. So we move on then to the second stage of this. And if I can bring you over here, we now take the theory of this one step further. So again, momentum is mass times velocity. So here we have the symbol for momentum. It is rho symbol. Very similar to density. It's kilograms per metre per second. And again, this is a unit you'd have to work out in the exam if you were asked it. And momentum is a vector quantity. So it's got size and direction. Now that's another important one to remember, particularly if you've got 2 momentums to deal with and the objects are going in different directions or the same direction. So when one object hits another object, we can say m1v1, the mass and the velocity, equals m2v2. And that's what we were trying to do over here. And hopefully without the sun getting too far in our way. Excuse me a moment. Then we then have consider a bullet. I don't know if you can see that with the reflected light. Consider a bullet. Mass of 1 gram is fired into a 500 gram mass which moves back at 0.5 meters per second. So it's a rifle. It's being shot into a stationary mass. Usually it's on a little trolley, and the stationary mass moves back. M1v1 equals M2v2. So the bullet, that's the 1, times its velocity. We don't know that. It's very hard to measure a moving bullet. A, it's dangerous, and B, you can't see when it's gone. So therefore we're going to try and use this system to work this out. It made a 500 gram mass move 0.5 meters per second. So if I rearrange my equation like I did in the last video thing, the V1 stays where it is, the 1 will go down underneath. I've moved it just for the sake of argument so you can see it. 500 divided by 1 times 0.5, and that gives you the velocity of the bullet was 250 centimeters per second. Now that's quite a clever way of using the momentum argument to work out the velocity of something which is very difficult to measure in real life. Bullets are notoriously difficult to measure because you simply can't see them. They go far past you too quickly. So bear this whole experiment in mind, please. I want you to try and do this at home. You need 2 bottles and 2 pieces of string. There is a health and safety aspect here. I do not want to find any students have been killed in their homes because the chair fell on their head, or because bottles fell on their head, or some other thing like that. But it should be possible in your house to make these things come together, possibly hanging from stairs if you have a stairwell. It's going to be down to how you make this work. It's resilience in science, isn't it? And what I need you to do, please, is to set the experiment up. And if you look back over here at the experiment, you can see, well, these are the results I got. I'd like to see whether you can get this. This again is one of these required practicals. They're going to ask you about this, and we may never have a time to cover it ourselves in the lessons. I would expect you to do this about an hour to do the experiment by the time you set it up, and probably about half an hour to write it up. Simple method, easy enough. Diagram of it all being put together, and then most importantly your results, a conclusion. I'd like to know how you've dealt with accuracy, and can you get better than my 12% ever? Do have a go. It'll get you out of your seats again, and as I said in the last video, science is all about practicals. It's not done by reading out of books. This is to get you thinking, and it's to get you using materials around you, just like the old scientists did themselves, to see if you can carry out these physics rules. So remember this one. Momentum is mass times velocity. Thank you very much indeed. Enjoy.